All right, hey everyone. Welcome to the Ice Giant System seminar series. I'm Jody Burtis. We've usually got Mallory Kinchuk here as well. She couldn't make it today, but so I'll be filling in for her. I just wanted to let folks know, and I'll mention this again at the end, that next month in March, we'll be canceling the instance of the seminar series just because it overlaps with LPSC. So to give folks in the community a chance to go to that and not be overloaded by talks, we'll be canceling the March instance, but we'll be back up in April. So I'll talk more about that at the end during the kind of community news part of this seminar series. But today we've got Dr. Tom Nordheim giving us a talk. So Tom Nordheim received his PhD in space physics from University College London, where he studied charged particle interactions at unmagnetized planetary bodies using data from the Cassini and Venus Express spacecraft. He subsequently joined the astrobiology and planetary chemistry group at the Jet Propulsion Laboratory as a NASA postdoctoral fellow. There, he researched the radiation chemistry of icy worlds such as Europa and Enceladus and investigated the survivability of potential biosignatures on their surfaces. After completing his postdoc fellowship, he stayed on at JPL as a staff scientist and deputy director of the JPL Ocean Worlds Laboratory, working on mission concepts for the exploration of Uranus and Neptune, including Triton, which was a finalist in the most recent Discovery mission call. In January of 2024, so just last month, he left JPL and joined the Johns Hopkins Applied Physics Laboratory, which we're very excited to have him, as a senior professional staff and manager of the magnetosphere-ionosphere coupling section. So yeah, Tom, you got your slides up there. I'll turn my camera off just so that the focus is on you. And folks, feel free to put questions in the chat if you'd like. You can use the raise hand feature. There will be a good period of time at the end for questions and discussion as well. But yeah, go ahead and take it away, Tom. Thanks for being here for us.
Thank you, Jody, and thank you to both you and Mallory for inviting me to give this talk. And yeah, I think I'd prefer, I've timed my slides for about 30 minutes. So if you can drop questions in the chat, and then we can discuss those at the end after the talk.
Great.
So I'm here today to talk about moon-magnetosphere interactions at Uranus and Neptune. And I'll start by prefacing that it's a big topic. I'm not going to give an exhaustive overview today, but what I wanted to give is kind of a flavor of why we think this might be an important topic at both Uranus and Neptune, with some examples from systems that we know a little better, especially Saturn. And so to start off here, so of course we know we have the 4 giant planets. Each one of these has a strong magnetic field, it has a respective magnetosphere, and it has a series of satellites, many of which orbit within those magnetospheres. And so that's really the top level context for moon-magnetosphere interactions is that we have these moon systems that are orbiting inside this magnetosphere, this essentially plasma bubble that exists around these planets. And so, of course, we know that we have a series of icy moons, icy worlds in our solar system. Many of these orbit around these 4 giant planets. In fact, most of them do. And then we also know that many of these icy worlds we know or strongly suspect to be ocean worlds. So they have subsurface oceans beneath their surfaces. So the green check marks here represent the ones I would say that we know have subsurface oceans. You could argue that maybe Mimas just joined the fold just recently with a paper that came out in Nature talking about its subsurface ocean. But I also want to say here that these green check marks, they're not because we've carried out an exhaustive investigation of all these moons. It's because these are the ones we know at the moment from the limited data we have. And so it's possible that some X number of years from now, there will be a lot more green check marks on this page. Now, in terms of charged particle bombardment, so these icy moons, many of them atmosphereless, airless bodies, they're exposed to these charged particles from the host magnetosphere of the planet that they orbit. And so these charged particles can be electrons or ions, so protons or heavy ions. They strike the surface and they cause different chemical and physical effects to the surface, including things like amorphization of crystalline water ice, sintering of ice grains where they fuse together, surface charging and a kind of electrical phenomena, and radiolytic modification, so chemical modification of the surface of these icy bodies. Now, this incident charged particles can also create sputtering, either directly or indirectly, and plasma scattering, which can create ejecta, essentially. So that's both neutrals and ions that populate exospheres around these bodies. At least the airless or bodies with tenuous atmospheres. There's this effect of creating these exospheres from the sputtering. And I want to say here, just to clarify, that the sputtering doesn't have to be direct sputtering. It can be radiolysis and then subsequent diffusion of gas molecules out of the ice as well, which we think is an important process there. So in summary, we have these various different effects that can be created by this charged particle bombardment of these icy moons. Now, how does that exhibit itself in the real world? Right, so I want to start with Saturn, because the Saturn system in some ways is the simplest case study here. It's got a strong magnetic field, but it's got a negligible tilt of its dipole magnetic field axis relative to its rotational axis. So it's kind of pretty much perfectly axis symmetric and aligned. It's got a major internal plasma source, which is Enceladus, that leads to pretty high peak plasma densities and a plasma composition that consists of these heavy ions, these water group ions. And it's got moderate electron radiation belts, up to about 10 MeV energies, at least that we know. And that's in comparison to Jupiter, which has very, very intense electron radiation belts. Now, the first effect that we'd expect from these moons orbiting inside the magnetosphere, in this case of Saturn. So you have the moons orbiting at their Keplerian orbital velocity, and then the magnetic field rotating with the actual planet. So that means that the magnetic field is actually rotating faster than the orbital speed of the moons. And because the magnetospheric cold plasma, it's carried by that magnetic field, it co-rotates with the magnetic field, it means that this magnetospheric cold plasma is constantly overtaking the moons. And so in this case, you see here this cold plasma overtaking the moon Tethys along its orbital trailing hemisphere. And so you can think of it almost a bit like a water in a stream flowing over an obstacle that pokes out. And so one effect that we see here, actually in the Cassini remote sensing data, so we see in the Cassini ISS filter data, so those are camera images of the surface, and we actually see this bullseye kind of pattern, darkening pattern, that seems to correspond with the expectations for this cold plasma bombardment, which creates this kind of bullseye. So a very interesting link there between the magnetospheric plasma bombardment and an observable surface effect. Now, when we go to higher energies, those particles are no longer just simply co-rotating with that magnetosphere. They're also an important part of their motion. It's this very rapid bounce between these magnetic mirror points in the magnetic field. And so what that means is that their bombardment onto the surface will be much more complex. Again, here for Tethys, what this means is that these electrons are rapidly bouncing along field lines. As soon as that field line approaches the trailing hemisphere, they kind of immediately precipitate into this kind of lens-shaped pattern concentrated near the equator. Now, because of the magnetospheric drifts, when the energy of those electrons increases above about 800 keV, those electrons start to gradient curvature drift in the opposite direction. And so they'll be encountering the moon from the leading hemisphere. And that's really just an effect of kind of adding up the orbital speed versus the various drift speeds. And so the effect of that is that you have, again, this lens-shaped region, but on the leading hemisphere as well. And again, in the Cassini remote sensing observations, we actually see this. I don't know if you guys can see this online, but there's this thin kind of lens-shaped color anomaly right at that leading hemisphere equator. And this is shown even more drastically in the thermal infrared from the Cassini Sears observations. So this is looking at surface temperatures at Tethys. We're kind of centered, you see the leading hemisphere right here, and you see that there's this kind of Pac-Man shaped anomaly, these really strong gradients in surface temperature. And we think that the reason for this is because of these energetic electrons. And so here you can see here, you see this thermal anomaly both on Mimas, which is the innermost major moon of Saturn, and Tethys, which is just the exterior of Enceladus. And we see these strong thermal inertia, these strong thermal anomalies on both moons. Here is shown a prediction of access patterns for energetic electrons at Mimas. And these patterns really correspond very closely to the gradients we expect in the electron flux to the surface, and really pretty remarkably so. And so what we think is going on here is that we think that ice grains in that surface regolith, they're initially, quite fluffy. There's limited thermal contact between the necks of the grains. But as you have these electrons bombarding the surface, they mobilize molecules at these necks. And over time, that electron-induced diffusion at the necks ends up growing the contact area, which changes the thermal properties. So it's a really neat, very strong example of a moon-magnetosphere interaction where you actually see pretty much a one-to-one correlation between the bombardment pattern and a surface effect. Now, so that's Saturn. We have this low energy plasma, we have these high energy electrons. Now, going to Uranus. Uranus is very, very different from Saturn. Again, it's got a strong magnetic field, but the tilt of the dipole versus the magnetic dipole versus the rotational axis is almost 60 degrees. And so you see some cartoons of that here. We have these really interesting and unique geometries of the magnetic field relative to the solar wind direction, which changes then depending on what rotational phase and season Uranus is in. So you get these really interesting geometries that you don't really get anywhere else, except for basically Neptune, which I'll talk about later, but has somewhat similar geometry. We have, of course, very limited information about Uranus's magnetosphere from the one Voyager 2 flyby in 1986. That seemed to indicate that there was no internal plasma source, but I would argue that the jury is probably out on that still. We have very limited data set. It saw peak plasma densities of only about a few per cc, which is relatively low. And the plasma composition, which again, from those preliminary analyses of the Voyager data seem to indicate only protons and no heavy ions. But again, I think the jury is somewhat out on that still. However, what was seen was very intense electron radiation belts with energies up to 10 MeV or so, and a 1 MeV electron flux at the highest intensities that were seen were comparable to that of Jupiter. So that's really pretty surprising. And so that indicates that charged particle radiolysis, especially from energetic electrons, actually may be pretty significant at Uranus. Now, Uranus has a series of 5 large classical satellites, and I'm showing 3 of them here. This is Miranda, innermost and smallest large classical satellite here, neighboring Ariel, and then Titania, which is one of the large outer classical satellites here. All of these are fascinating for different reasons, and I don't mean to say that the other 2, Umbriel and Oberon, are not. But starting with Miranda, Miranda has this incredibly unique and disrupted surface appearance. Some early theories suggested that it may have been catastrophically disrupted by a giant impact. That's no longer the favored theory, but we think that there may have been really intense periods of heating, tidal heating of this body that's really created this very, very interesting and disrupted surface. We see these corona regions, which are these kind of chevron-like surface features. And some of these are associated with very young surface ages. And so there's strong indications of some geologically recent activity here. Ariel, also very fascinating looking. It's been extensively tectonically deformed. You can see these extensive rift canyons here. Interestingly as well, some of these rift canyons seem to have kind of been filled in with some smooth material. which has been interpreted as being suggestive of cryovolcanic deposits. Again, very fascinating. Again, a relatively young surface as well. Titania, on the other hand, much larger satellite, generally much older surface. But even so, some significant tectonic features, and also importantly, some previous theoretical studies of thermal evolution of this moon have suggested that it could have a subsurface ocean to present day. And so we have some really interesting hints of geologically recent activity at Miranda and Ariel, which may hint that they are ocean worlds or have been recently. We have some strong theoretical reasons to think that Titania, largely because its larger size, would still have a subsurface ocean. And so this is a system of containing multiple possible ocean worlds, which is pretty exciting. Now, very interestingly as well, we've seen these volatiles, namely CO2 and possibly ammonia, on some of the Uranian moons. Very strongly, in both cases, seen on Ariel. So this is showing on the left-hand side from Cartwright 2015, some distinctive CO2 absorption bands that are seen on Ariel, which are only generally visible if you have very strong concentrations of CO2, really thick layers of CO2. And so this is really showing that there's some really significant CO2 deposits on the surface. Shown here in the purple is the leading hemisphere and the trailing hemisphere. And you can see here that these CO2 deposits the absorption features for them are much stronger on the trailing hemisphere than on the leading. Now, here shown in a plot from Cartwright 2020, we've also seen this 2.2 micron absorption feature that may be due to ammonia or ammonia-bearing species, or NH-bearing species. There we saw a possible suggestion that these ammonia-bearing species may be associated with parts of the surface that were in the Voyager images identified as being possibly cryovolcanic. But again, I should really emphasize here that we're looking at ground-based, non-spatially resolved observations of the surface. So it's difficult to really make that correlation. But the key point here is that both of these volatiles, generally, these volatiles are not stable over geologically long timescales. And so could they be tracers of recent geologic activity? For example, very notably ammonia. Ammonia hydrates have been known from lab experiments to be decomposed relatively quickly from charged particle radiolysis. And so we expect maybe at most 1 million year timescale lifetime for these on the surfaces of these Uranian moons. And so seeing ammonia is both puzzling and perhaps suggestive of some recent replacement, maybe from some recent geologic activity. And so, however, for the CO2, there's a more complex story going on as well. And so this is shown here, a CO2 band area versus radial distance from Uranus. So you see each one of the moons here with their leading and trailing hemispheres indicated. And so what you see very strongly is that Ariel really stands out, and that really there's a consistent trend of the CO2 mainly being concentrated at the trailing hemispheres, perhaps most strongly at Ariel, but there is still a statistically different distribution, hemispherical distribution on each one of the moons. So this suggests both this leading trailing trend and the radial distribution out from Uranus suggests that the CO2 might be radiolytic in origin. And so that is created from radiolysis of water ice and some carbon-bearing species, perhaps amorphous carbon, on the surface due to magnetospheric plasma bombardment. However, we also have another example of an icy body, comparable icy body that has huge quantities of CO2 localized on the surface, and that's Enceladus, which we know has the CO2 concentrated on the South Pole, here in the plot from Combe et al., concentrated on that South Polar terrain and sourced from venting at the Tiger Stripes. And so while the CO2 appears to follow a possibly magnetospheric origin, sort of the expectations for that, there are also other possibilities. And very interestingly as well, there's this recent paper by Ian Cohen and team from APL that reanalyzed some of the Voyager 2 sort of superthermal energetic particle measurements and found that they were actually consistent with a possible source of energetic ions, so a source of plasma somewhere between the orbits of Miranda and Ariel. If true, then this may also be an indication that there may be some sort of geologic activity, maybe some sort of active process going on there. But again, many questions. More recently, we've been carrying out some work led by graduate student Stephanie Menton and her advisor Mike Sori at Purdue University, looking at what happens, if you just have CO2 molecules on the surface, if you initiate them and let them thermally and ballistically transport across the surface, what happens? What kind of distributions do you see, and do they match the observations? And the take-home message there is that these CO2 molecules tend to hop away relatively quickly from their origin point. And so really on the timescale of a few Uranian years, which is not that long on geological timescales. So that suggests that the CO2 distribution that we see concentrated on that trailing hemisphere of Ariel, it seems to be consistent with either a very recent production mechanism sometime within the last 1,000 years or so, or an ongoing production of CO2. So that, again, could be consistent with a magnetospheric origin, or it could be consistent with some sort of active geologic process that produces this CO2. Now, in terms of understanding the charged particle bombardment, though, in the example I showed for Tethys, you have this really nice axisymmetric alignment of the magnetic field and the rotational equator. And you can think of the plasma as this kind of stream just flowing over the trailing hemisphere of Ariel in this case. However, as we also saw, there's this huge geometric offset between the rotational equator and the magnetic equator for Uranus. And so shown in this graphic from Corey Cochran at JPL, so what this is showing is a visualization of the magnetic field of Uranus with the orbits of the three innermost moons, Miranda, Ariel, and Umbriel, kind of superimposed on that. And what that's showing is that basically as this magnetic field kind of tumbles around the moons, they sample these really wide arrays of different magnetic environments. This is shown a little differently here. So this is showing the magnetic L shell that each moon visits over time. And so what you see here is that for these three innermost moons, you have huge ranges of magnetic L shells. So think of them as magnetic environments that these moons visit. And that has a consequence both geometrically, but also in terms of the charged particle environments that they occupy. And so on the right here is shown a profile of the electron differential flux at different L shells. And what you see here is that there are order of magnitude variations in intensity depending on which L shell you're at. And so really, this environment is incredibly variable. And then geometrically as well, so this is showing the results of particle tracing for electrons at Ariel. So what this is showing here is the expected surface access of electrons to Ariel surface, and this map is centered on the trailing hemisphere here. Sorry for the slightly confusing coordinate system. So here it's shown for a perfectly axisymmetric aligned magnetic field like you have at Saturn, and then you increase that tilt from 30 degrees to 60 degrees. And then with the realistic, kind of best guess Uranian magnetic field model, or best constrained, you actually see that due to this tilt of the magnetic field, that access of electrons to the surface really changes, and you no longer really expect some of these electrons to be bombarding the trailing hemisphere, as you might expect from that axis-symmetric kind of intuition. Here specifically are shown some access patterns for 10 keV and 1000 keV 1 MeV electrons. And again, you actually see that seems to be a bit of kind of a minimum in access at the trailing hemisphere for these particles. And so these results suggest that energetic electron bombardment is actually not favored at the trailing hemisphere, which does not appear to match the observed distribution of CO2 concentrated in that location. And so this may be seen as counting against the hypothesis that the CO2 is magnetospheric in origin and may support the idea of an active endogenic source instead. But I should mention that there are a lot of uncertainties here still. Very notably as well is an uncertainty in the energetic particle fluxes. If you make different assumptions about the flux spectra, that can change whether or not you get an energy deposition enhanced at the trailing hemisphere or not. So I should really emphasize that there are a lot of uncertainties here, but nonetheless, it's an interesting result, I think. Now, another aspect of moon-magnetosphere interactions that I wanted to touch on really briefly is the fact that we have these Uranian moons orbiting in this highly variable magnetic environment. So that means that they have a strongly time-varying magnetic background field. And so what that means is that if we wanted to look for subsurface oceans at these moons through magnetic induction, these are very well-suited targets for that. And here are some plots showing different examples of magnetic induction signals for different ocean conductivities at Miranda and Ariel from a paper by Corey Cochrane et al. And just in summary, what he found was that at the 3 innermost Uranian moons, if they have subsurface oceans, they should be relatively readily detectable using magnetic induction, even from a single flyby. And even if they had surprisingly intense ionospheres. So that's that's the Uranus system. I want to move on to Neptune. So Neptune, relatively similar to Uranus in some ways. We have this strong tilt, dipole tilt relative to the rotational axis. Unlike Uranus, we know that we do have an internal plasma source, which is Triton, which supplies a small amount of heavy ions, notably nitrogen ions, likely nitrogen ions, to the Neptunian magnetosphere. It has weak electron belts, much weaker than what we see at Uranus, and much more along with expectations. Neptune, of course, is very different. It only has one large moon, which is Triton. It's in a retrograde orbit, and surface composition, atmospheric composition is Pluto-like. We think it may be a captured Kuiper belt object that maybe catastrophically disrupted the original Neptune moon system. It has a global atmosphere with significant surface pressures, I would say. It has a very young surface, including this cantaloupe terrain, extensive ridges, as you can see on the image here. And we think it's possible that this may have a possible present-day subsurface ocean. And one interesting thing that Voyager 2 saw at Triton when it flew by in 1989 is actually the first ever observations of plumes on an icy moon. Actually, before Enceladus, Voyager 2 actually observed these actively erupting plumes, as well as evidence of past plume activity on the surface. So there's clearly some significant activity here, but the question is if this is rooted to some subsurface ocean, or if it's only due to some near-surface effect, like a hypothesized near-surface solid-state greenhouse effect. Now, also very interestingly, Voyager 2, during its one flyby of Triton, also carried out these radio occultations. You can see a geometry of the occultation measurements here and the resulting ionospheric profiles here. And they very surprisingly found that the ionosphere was very, very dense. about 5 times 10 to the 4 per cubic centimeter peak ionospheric density. And so that's about 50 times that of Titan's ionosphere. And Triton is at 30 AU, so should have minimal solar input, much less than at Titan. And interestingly, New Horizons during its flyby at Pluto, at which point Pluto was located at a similar distance from the sun as Triton, found no measurable ionosphere at Pluto. And so this is a very interesting comparison as Pluto and Triton are similar solar distance, very similar bodies, but Triton has this really intense ionosphere, large densities. And so that really indicates that Triton's ionosphere may actually be driven by Moon-magnetosphere interactions instead of solar input. We carried out some work on this using some modern models, seeing if we could explain the ionospheric densities at Triton. And we investigated the input from different sources. Shown here is an output from our model looking at magnetospheric electrons versus galactic cosmic rays versus solar UV photoionization. This, of course, is only showing the instantaneous ion production rate. And of course, there's subsequent chemistry. But what this confirms is that magnetospheric energy input is likely important and possibly dominant energy input to Triton's ionosphere. We took a step further than this, and we coupled that energy transport code into a 1D photochemical model that was previously applied to Titan and Pluto. And so that we used that to try and get to a steady state ionospheric density from those different inputs, because that can actually be compared to those Voyager 2 radio occultation measurements. And what's shown here is the peak ionospheric density versus the energy input. And what we've done here is that we ran a bunch of different cases. So first we looked at the case of solar UV input only at solar minimum and maximum. Okay, that didn't even come close to replicating the peak ionospheric densities that Voyager 2 saw at Triton, which are indicated up here. Then we looked at the best guess electron spectrum at Triton from the Voyager 2 flyby. Sorry. Again, that didn't even come close to replicating the peak ionospheric density seen by Voyager 2. And so then what we started doing is just looking at how we'd need to change the electron input spectrum to get even close to the densities that we saw. And so we had to increase the energy input from the magnetospheric electron spectrum by more than 2.5 times to get close to those peak densities. But we should say here that while this point down here is kind of a best guess spectrum, Voyager 2 never directly measured the magnetospheric environment near Triton itself. And even this best guess spectrum, there are a lot of assumptions made there. So we really don't know that input spectrum. Now, one of the ways that we wanted to test this hypothesis of the magnetospheric input to the ionosphere was the Triton Discovery mission concept. It was under consideration in the NASA Discovery program. Unfortunately, it was not selected this past round. It would have launched in 2025 and arrived in 2038. It would have carried a particle and field suite and would have actually characterized the ionosphere of Triton by flying into the ionosphere, very deep into the ionosphere to low altitudes of less than 400 kilometers, which would have enabled it to resolve this question, what drives Triton's ionosphere. Now, so in summary, I hope I've given you a flavor that moon-magnetosphere interactions are vital to our understanding of icy moons, both in terms of their surface, their atmosphere, their ionospheres. We know that this moon-magnetosphere interaction is known to cause significant effects, for example, at Saturn's moons, like this Pac-Man feature seen at Mimas and Tethys. At Uranian moons, we see these very interesting surface volatiles that could be a tracer for activity there, but we need to understand the role of the magnetospheric input. At Triton, we think that the really unexpectedly intense dense ionosphere there could be powered by Neptune's magnetosphere. And we've seen that both Uranian moons and Triton are good candidates for ocean detection using magnetic induction. However, I want to emphasize that we really have very limited data available, and that really new missions are strongly needed to both systems to answer these kind of outstanding questions. So yeah, with that, I'll open up to any questions folks might have.
Awesome. Thanks so much, Tom. Yeah, that was a really incredible presentation. Very thorough. I wish there was a, oh wait, there is a clapping. Where is it? There it is. Clap. There we go. Clapping feature. Yeah, I see some. I see some clapping in clapping in the participants window. So yeah, thanks so much, Tom. Great presentation. We've got a few questions in the chat here. Folks, feel free to continue posting stuff in the chat. If you want to ask Tom your question directly, you can use the raise hand feature, unmute, put your camera on if you'd like, things like that. But I'll start with these questions in the chat first for you, Tom. So first question here is from Riley DeColibus. Wouldn't the thermal/exospheric migration of CO2 on aerial bring it to the central trailing hemisphere anyway, as shown earlier? We do see leading trailing asymmetries in CO2 on the other moons too.
Yeah, that's a great question. And I have to say, that isn't my area of expertise, that thermal modeling. Unfortunately, Stephanie and Mike aren't online right now, but from my understanding of their results, if you created CO2 at the center of the trailing hemisphere, what they're finding is that it would migrate away relatively quickly. And that's a consequence of, we have these really interesting geometries at these moons, as you know. And so we don't necessarily expect the CO2 to be stable there over long time scales unless it's being continuously produced. But yeah, that's a great question.
Great, thank you. All right, next question so is from John Cooper. So Tom, do you agree that drift resonance energies for electrons are at tens of keV, so most energetic electrons do avoid the trailing hemisphere?
Yeah, absolutely. That's a really good point, Hank. And that's why looks like there's a limited input from these energetic electrons onto that trailing hemisphere. And that's a big part of it, is that for the rest of the folks online, at the Saturnian moons like Mimas and Tethys, we have this transition energy from the leading to trailing hemispheres. There, it's about 1 MeV. At Europa, that resonance energy, that transition energy is about 20 to 25, 30 MeV. But at aerial, that transition energy, where the electrons start approaching the leading hemisphere instead of the trailing hemisphere, that happens at very low energies. And so that means that just a very limited amount of that distribution, electron distribution, can access the trailing hemisphere.
Great, thanks. All right, so we got next question here is from Thomas Coverstone. This was actually the question I was going to ask, so glad you asked it, Thomas. What additional interesting data could you use from a future spacecraft mission to Uranus/Neptune?
Oh, that's I feel like that could be a whole other 30-minute talk, but absolutely, strong particle and fields measurements, both at low energy plasma to high energetic particle measurements with ion composition measurements. I think that's really key. And I think this recent paper by Cohen et al. Looking at possible sources of plasma from the moons, really emphasizes that we need a plasma composition spectrometer, plasma and energetic particle composition spectrometer. And the other side of it, very strongly, I think we need some sort of near-infrared imaging spectrometer that can look at the surface composition of these moons, because that's really looking at those correlations between the expected magnetospheric bombardment patterns, the geology, and things like the distribution of these surface volatiles. That's going to be really key, I think, to unraveling these mysteries of what's really creating these volatiles.
All right, perfect. All right, so next question here is from Michael Lucas. So regarding the 59-degree dipole tilt at Uranus, any evidence that this tilt varies over solar system timescales? If so, could this explain why your models suggest that electron bombardment at aerial is not enhanced at the trailing hemisphere?
Yeah, so that's a great question. And again, I have to say that's not my area of expertise. But I'll say that wouldn't expect that tilt to vary over shorter timescales, let's say 1 million years or thousands of years. And some of these species, for example, the ammonia, we don't expect it to stick around for longer than that. And so if we're talking about billion-year timescales, I would definitely have some big questions about the stability of that geometry. But over the shorter timescales, I would expect it to be not varying as much. But many major questions about that still, and we only have that one flyby, so it's hard to say.
Definitely. All righty, next question here from William Moore. To follow on that, which I think that is referring to Riley's original question about thermal and exospheric migration of CO2. I believe it. Correct me if I'm wrong, William Moore. Would a more multipolar magnetic field geometry also have an impact on the bombardment geometry?
Yeah, so that's a great question. One thing we find, so if you look at this map here, which is bombardment patterns onto aerial for electrons with different magnetic field geometries. So these first three are actually just a simple dipole with different degrees of tilt. And this last one introduces this more complex multipolar field. So you see between the 60-degree tilted pure dipole and the more realistic field, it does introduce some more complexity into that bombardment pattern. So for example, it gives some more access of electrons to the trailing hemisphere as opposed to the dipole only case. So even at Ariel's orbit, where we expect the field to be mostly dipolar, we still see some variations.
Those are the only questions I'm seeing in the chat now. If anyone else has any more, definitely feel free to post them, or you can just use the raise hand feature if you'd like to have a conversation face to face or unmuting kind of thing. But unless I see anything else, thank you so much, Tom. This was such an incredible presentation. It was really thorough, and I definitely learned a lot. And in the last few minutes before we break, I'm gonna throw up the community news slide that I prepare each month. So let me just do that real quick for folks that have a chance to stay on for another couple minutes. Let me see if I can bring it up. I believe it's here. We go. Right. So if you're new, this is something that we do every month just to sort of make sure that the community is staying involved, staying up to date on what everyone's doing, and just kind of ensuring that everyone knows what's going on in the community. There can be a lot of newsletters and news articles and the Pen and the DPS newsletter and all these different things. And it can be kind of hard to sort of sift through everything and make sure that you're getting all the information. So I every month I try to put it all in one place for this particular community, just to kind of make things a little easier to digest. So this is kind of my version of that for the Ice Giants systems community. So first of all, like I mentioned at the beginning, our March instance of this seminar series is going to be canceled. So you all likely have a recurring meeting invite on your calendar. So if possible, remove the March instance of it. I'll send out emails as we get closer to the date just to remind everyone to do so, just so that we don't have folks tuning into an empty Zoom room. But the following month in April, we're going to have Dr. Henrik Malin. I believe it was at some point last year, a few months ago, he was hoping to give a presentation, but I think he had sort of an emergency the morning of, so we've been able to kind of shift his meeting to April. And I'll pause real quick because I see that there's a hand raised. Yeah, go for it.
This is John Cooper. Hi, Tom. I just wanted to know, are you still at JPL, or have you already moved to APL? When are you going to do that?
Oh, hi, John. Yeah, I'm officially working for APL now. And for the moment, for the next couple of months, I'm working remotely from Pasadena, but then I'll be moving out to the Maryland area soon enough.
Okay, looking forward to seeing you there.
Yeah, likewise.
Yeah, definitely. Super exciting stuff. We're excited to have Tom too. Alrighty, so yeah, and again, like if anyone has more questions for Tom, definitely go for it. Definitely feel free to raise your hand and ask questions. Couple more things. The Ocean Worlds Working Group, specifically the Science Goals Subgroup meeting, is tomorrow at 10 a.m. Pacific time. So that's 1 p.m. Eastern time. So let me just do this real quick. I apologize. So let me copy paste these into the chat because you all can't click on a screen share. So here's a massive text dump, apologies, but at least then you'll have the links. So that's in the chat there. There's also, I thought particularly relevant to this group, there's an Exoplanets in Our Backyard. There's a save the date out. I thought that was a little, could be relevant for some folks in this community. There's also a couple researcher and associate professor positions at the University of Oslo for the Center of Planetary Habitability, NASA postdoc program fellowships. I believe there's 3 that have 3 deadlines a year. So we've got one coming up in just a couple weeks. And then, of course, the Uranus flagship workshop that Goddard and APL are joint hosting at Goddard in May. Registration is open, and early career travel awards are also applications are open for that as well. So that you should have that link in the chat too. So we're pretty stoked about that. Other than that, I think that's everything I've got. If there are last minute questions for Tom, feel free to post them in the chat, open your camera up, raise hand, things like that. But if not, I can kind of close things out and give you all a few minutes extra for your day to kind of shift over to your next meeting. So thanks so much, everyone, for coming. This has been really great. And thank you again, Tom, for an incredible presentation. It was really wonderful. But if I hear nothing else, then I will, I'll close this Zoom out. So thank you, everyone. I will see you in 2 months. So, yep, have a great week. Bye, everyone.
Thanks, everyone.